All right, guys, welcome back. Okay, so quickly, I want to show you something because a lot of people don't know that Quicksilver series has a very simplified calculation sheet. You know, most of the times when you do design, the some organization demand that you also submit your calculation sheet, and Quicksilver series makes it so simple that even if you're not really sound on your structural design, on your theoretical structural design, it makes the calculation sheet so simple enough. Okay, so for those who don't know Quicksilver series, I'm going to open it so quickly so you see Quicksilver series how it looks like, and after then I am going to show you how the calculation sheet looks like and how simple it looks. Okay, so let me quickly launch the Quicksilver series software. All right, so this is a Quick Structure 9.0. If you need this software, you can always contact me. I have the cracked version you can enjoy. It's a simple software, straight to the point. But I want to advise you, when you're having a bigger, complex project, you can use Civil Series. Okay, you can use Quick Civil Series. I would prefer you use a software you can have maximum control. Okay, because in Quick Civil Series, there is limited control to the things you can do. Okay, so but it's a quick thing for a quick job. Okay, so I click on New Project. All right, so yeah, so these are the parameters you can easily quickly change. So I believe a lot of people have gone through my previous video. Okay, so I'm not going to be doing anything here. So this is how it looks like. All right, so let me quickly show you how the calculation sheet looks like. So this is the calculation sheet for Quicksilver series. Okay, so I want you to see something. For those of you who are good in structural analysis, you easily understand this. Okay, so first, the page is made so simple. Company details you put there, project name, you include subject, all of that. Made by, checked by. Okay, who did the design, who checked the design code. So all of this you can impute it before generating the calculation sheet, so you don't have to come put them manually. Okay, so you now come to design calculation sheet. Then we look at basic design information. This design was done on this date and this is the time. Okay, so basic design information, you can see my imposed load. Okay, that's the live load. You can see the finishes, you can see partition allowance, you can see my soil bearing capacity, slab design FCU, that's characteristic strength of concrete, or you can call it compressive strength of concrete. So I'm having 25 Newton per millimeter square, and for my beam, I'm using the same thing. My Fy, that is the tensile strength of steel, is 410. Okay, I like using 410. I don't like going something higher than that. Okay. Then you also have design for beam design FCU for beam. You also have Fy for beam. You have Fy for column and FCU for column. Okay, so in most cases you may decide to say I want to use grade 30 for columns, and maybe use grade 25 and use grade 25 for my beams and my slab. So you can control it here. Same thing with your foundation. Okay, density of concrete, just like we know, 24 kilonewton. So we go further. Okay, so now the next thing is panel one, slab loading moment analysis reinforcement design. So this is the subject. So based on my panel that I designed, my slab thickness was 150. Okay, characteristic imposed load, just like we said, QK 1.5, finishing, partition, and all of that. Then you can also see the calculation for the self weight. Okay, so thickness times density. Then dead load is calculating the dead load for me at 1. So 3.6 plus 1.2. Okay. So 1.2 was my partition allowance. Okay, don't forget. Let me take you up again so you see. Okay, finishing was 1.2, then partition allowance was 1. So 1.2 is for finishing, then 1 is for partition allowance. So this is dead load. Okay. This is dead load GK. So this has been calculated. Then you now come to design ultimate load. Okay, don't forget that my design imposed load is 1.5. Okay, because this is a residential building. So design ultimate load is where you are now converting from serviceability limit state to ultimate limit state, so you can use that value to calculate for your moment. All right, so So we now have 1.4, which is the unit. This is this times GK, which is the dead load, plus what am I doing all of this? There's no need for that. All right, so you can see all of that. Then you also see the total design load based on what we've calculated. You can see the length of my short span, the length of my longer span based on the geometry of my slab. Then your Ly over Lx. So this is where you decide if it is a one-way or two-way slab. And we also come to positive moment at mid-span, okay? Don't forget at mid-span you have positive moments and you also have negative moments, okay? So at short span, mid-span, okay? So from your structural design you should know this already. I don't have time to explain that. Then what again? Reinforcement design, applied moment 2.7, that's very little. FCU this, that. Then effective depth is 112 millimeters. Type of steel, high yield steel, and type of steel high yield. Then area of steel minimum, which is 0.13% BH. Okay, so 0.13 BH, 0.13% BH. So B is 1000 because you're considering a 1 meter span of slab. Okay, 1 meter by 1 meter times 150, which is the thickness. So okay, H is the thickness. So this is the minimum. So whatever I'm doing, I should never go below the minimum. Okay, so you also check for your K value, so you can always know if it's going to be a singly reinforced section or doubly reinforced section. So your K must always be less than 0.156, just the way you know your normal structural analysis. So that is it. Then you come to your lever arm, you calculate your lever arm, and then you get the value for your lever arm. You also check for your area of steel. Don't forget this is minimum. And when we calculated the required area of steel required is lower than the minimum, and so we can't take this, we must take the minimum. Okay, so as provided, bottom outer layer, blah 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 and all of that. So use y12 at 150. I can tell you y10 will, even y8 will work if you have a good y8 steel. All right, so the moment is very little on that span. Okay, so you now go to deflection check. These are all the things from your basic knowledge, you know them. Area of steel required, just like we did, provided is this, because you need to provide something that is higher than required. You can see the limit. This is very far from this. Okay, so basic span all over effective depth ratio, you get this from your code 26, depending on the support condition or the end conditions of your slab. You check if effective depth have been calculated initially. Then you also check for your m all over bd squared. Okay, and you get all of this value, then you throw it into your modification factor, and you quickly check to see if since modification factor is greater than 2, then you use 2, and at the end of the day deflection is good. Okay, because allowable ratio is greater than actual ratio, so check is okay. All right, so that has been done for just for mid span, positive moment mid span. You come again to positive moment at mid span. That was negative before, now positive moment at mid span. So it does this for all of them. So you end up having a whole lot of booklet at the end of the day. Okay, so this is for slab. So I'm going to take you straight to beam. Let's go quickly to beam. I think this is going to take a long time, so let me use this. Where are you? Oh, come on, man. Where is beam? Okay, good. So we are here. Let's quickly check this. Let's quickly check this beam out. Where did beam start? First floor beam 1. Okay. Alright, let's go up a little. I just want to show you how this guy does this design, and you're gonna like it. So if you need this software, you can always contact me as quick as possible so we can roll. Oh, where are you starting from now? Taking me too far. Okay, so let's quickly look at this. First floor element beam 1. Okay, this is a section 450 by 225, span 4. Okay, so let's see. Applied moment already calculated is 28.58 kilonewton for this span. Okay, and breadth of section 225, depth of section you see, cover to reinforcement FCU and FY. Length of span is 3662. It's not a large span. Okay, width of flange BW 225, thickness of flange HIF, which is 150. Assume diameter of tension bar, I'm assuming 16 mm. Assume diameter of link, which is 8 mm. Type of steel is IA steel. Area of steel minimum, still based on what we did before. So you can see it calculated there. Then effective depth of flange already calculated. So you have the effective depth of flange. Effective depth D is calculated 409. Okay, so effective depth, you've gotten it. So you can also check, further check for what do they call it? Check for you can further check for moment capacity. Okay, so you can check for the moment capacity. So when you're calculating for the maximum moment capacity, it must be greater than the moment gotten from the calculation itself. Okay, moment capacity of the section must be greater than the calculated moment. If it is higher, then you can possibly design this as a doubly reinforced section. Okay, but you have to be careful, because if the limits of the difference is too high, you may have issues with deflection. So that is also very important. Okay, so once you've checked moment capacity, the next thing you're going to be looking at moment capacity, the same thing as moment resistance. Okay, your moment resistance or moment capacity must be higher than your applied moment. If your applied moment is higher than your moment of resistance, it therefore means that that section has to be designed as a doubly reinforced section. Okay, so meaning that you're going to be having reinforcement at the top fiber and at the bottom fiber. That's to say, you're going to be having reinforcement at the compressive and the tension zone. Okay, then you also check for your S to know where your neutral axis falls. Okay, all right, so this is that and that and that and that and that. So lever arm has been calculated, X has been calculated 45.447, so meaning that the neutral axis falls within the flange. So as such, you can design this as a rectangular section. So that is that. Okay, so I just wanted to show you how the calculation sheet looks like. So you can go all the way down to the foundation. So you can see the calculation for the moment and shear forces here. Okay, so it's using fixed end moment uh, method. Okay, so it's using that for the calculation for the moment and the shear. Okay, so you can see that. You can also see the diagram for the moment and shear. So that is just that for Quicksilver series. So I take you back to Quicksilver series. So this is it. So you can always pick a panel, click. Okay, that is if you're not importing from AutoCAD. So you can always do it manually. You can check my previous video on Quicksilver series. You're going to see a full tutorial there. Okay, see you guys in my next video. Thank you.